Okay, welcome back to part three of section 6.4, where we're talking about the sampling distribution for means. Okay, here's a big example of all of this material. So it's the last example, but most important one. So it says the GPAs of all students enrolled at a large university have a normal distribution. So all of the GPAs of students have a normal distribution with a mean of 3.02 and a standard deviation of 0.29. All right, right off the bat, what this information is telling us that we've got a mean of 3.02 is the GPA and a standard deviation of 0.29 of all students. Okay, so part A, find the probability that one randomly selected student will have a GPA greater than 3.20. All right, now fine, that's part one. The key here is it says one randomly selected student. Okay, so we want the probability, of course, but the information is one randomly selected student will have a GPA greater than 3.20. Okay, look at part B. It says find the probability that 25 randomly selected students will have a GPA greater than 3.20. So I hope you're catching that these questions are really, really similar, but obviously there's a big difference. So look at the two distributions I've already provided for you. This is the big clue. Let me draw the first distribution in blue, since you know I like to make my bell-shaped curves blue from the original distribution. And for part B, I'm going to do this two questions kind of at the same time because I find them very helpful for kind of explaining the similarities and the differences. So what's the name of the distribution in part A? Well, because we're randomly selecting one student, what I want you to imagine is all of the students under the school are under the blue one. Every student has their own GPA, okay? That's what we're doing when we're doing the X distribution. So the average or the mean of the entire school's GPAs is 3.02. Okay, now what about part B? It's saying 25 randomly selected students. So this is our N is bigger than one situation. This is what triggers that we have to use the sampling distribution theory. Sorry, I can't spell. Sampling. Okay, what I want you to think about is, okay, for the sampling distribution, we're going to have that the central limit theorem tells us that the X bar distribution, that's the samples of all. Okay, what I want us to think about is this. So imagine somebody's GPA. Let's say my GPA is right in the middle. I have an average GPA of 3.02. It's just one individual. Okay, maybe my friend has a GPA that is one standard deviation above, which we can figure that out because we've got the sigma. Now, I'm not going to do the calculation. I just want you to follow along. If I put two dots under the sampling distribution under the same locations relatively, what do those two dots actually represent? Well, what I'm saying in the first dot, the one that's right in the middle, is if I grabbed a random sample of 25 students and took the average of their GPAs, okay, that middle dot, those averages are 3.02, okay? But that is way different than in part one. It's like a single student having a GPA of 3.02 versus the entire random group of 25 students, they're all going to have their own GPAs. But when I take the average, it's 3.02. Okay, and actually, why don't I calculate? Aha, I fixed it. So 3.02 plus the standard deviation of zero point 0.2, oops, 0.29 is, what happened here? I'm sorry, 3.02 plus 0.29, there we go. So 3.31. So that is this number right here. And actually, I'm glad we calculated that because what it's saying is the second blue dot, the blue dot that's right here, that blue dot basically is one student, and that one student's GPA is 3.31. Okay. What is the dot over here representing? It's still one standard deviation above the mean, but it's a different curve. Okay, let me zoom in a bit so I can write a little neater. Remember, so from our formula sheet, mu of x bar is the same as the population mean. So that's why these two numbers are the same. The standard deviation sigma of x bar, though, that is sigma divided by square root of n. And that's going to be, so we're going to do this calculation on the calculator, 0.29 divided by the square root of 25. This is a much different number. So let's do it. So it's, let's start off with my favorite button, alpha y equals 0.29 is my population standard deviation, and then I'm going to divide by the square root of 25. Okay, and I get this number, so it's really tiny. 0.29 was already small, but 0.058 is even smaller. So this is our standard deviation. So when I add that last number, 0.058 plus 3.02, sorry, I'm doing this off screen here, we've got that this number right here, our first tick mark, is actually 3.078 right here. So you can already see that the 3.31 was one standard deviation above, but that's with the original distribution. With the sampling distribution, where it's way more narrow, it's 3.078. So much closer together. Okay, why is that? Well, think about it like this. We're saying, okay, that that second dot, what that represents is a group of 25 students having a GPA of 0.078 as an average. Okay, and of course, if you think about it intuitively, well, you've got a big group of people. Because of that, most of their GPAs will be, close to the middle of the original distribution. That's why their average is still pretty close to the original distribution. Okay, that's what's happening here. All right, now let's go ahead and solve both of these problems. So part A, back to a single student, right? One. That means we use the original notation. We're going to say, okay, that one student, we're going to think of them as an X. Their GPA is bigger than 3.20. And 3.20, without trying to be super precise here, let's just put that bar right here, since I do want you to draw and shade. Okay, so I'll shade with my, with my shading tool here. But if you're doing this with just a pencil, you can of course use the little shading like that. All right, so visually that's our probability somewhere a little less than 1/2, but again, it's tough to predict the actual value. Normal CDF is the calculator instructions to compute probability, give it the lower value, 3.20, comma, upper value. Well, I don't see an upper value, so we have to give it a really large number. 1E99 is our upper value. Now here, what do we use for the mean? Because we're doing this with the original distribution, I am going to use the original mean and the original standard deviation in these calculations. So I'm going to put 3.02 for the mean and 0.29 for the standard deviation. Okay, so that's the original mean, original standard deviation, and we've got our lower and our upper values. Okay, let's calculate this. Second, vars. Oops, I'm not used to this digital calculator. Second, vars, there we go. Normal CDF, lower 3.20, upper 1. Time to use the dolphin button. Remember, it's this comma button, but the double E, the E. Second, comma. There we go, 99. It's my upper. The mean is 3.02. Enter. And the standard deviation is 0.29. Excellent. Double check that I entered the numbers correctly, and they look good. 3.20, 199. Okay, good. So here's our answer to part A. 0.27, sorry, 267. Okay, so a little less than 30%. Looking at our blue distribution in the shaded region, that looks about right. Okay, so watch what happens with part B though. What is it that we want to do for part B? Since we're doing a 25 sample, this is when it's the sampling distribution. So here's the notation. P of X bars are now bigger than 3.20. So the number is the same cutoff, but conceptually we're doing something totally different. So we're going to have normal CDF, since central limit theorem tells us that the X bar distribution, the red, is approximately normal. Lower value 3.20, upper value 1E99. Okay, so just like last time, because it doesn't really give us an upper value. Okay, then what do we do? Well, here is where we've got a difference. We've got lower, upper are the same, but when we enter the mean, we have to enter the mean of X bar and the sigma of X bar. So we actually did these already when I was kind of explaining what's going on here. So here they are. But the way I recommend that we enter this is actually the unrounded number. So let me actually recommend, we're going to use this one. So the mean is, and I'm going to do it in red just to kind of visual clue that it's the sampling distribution, comma, although the central limit theorem tells us that those two numbers are actually the same. Now for the standard deviation, we're going to do 0.29 divided by the square root of 25. This is how I recommend we enter it into the calculator. Okay, so let's do the calculation, look at the number, and then I'll kind of do the drawing afterwards, because I find that sampling distribution, the questions are a little bit harder to visualize. Okay, second, vars, normal CDF, lower, upper are the same, the mean is the same, and the standard deviation, here's what we have to do. it's actually 0.29, and then we're going to do the divided by button, second x squared, so that we can do the square root button, and now we'll enter our sample size. So this is the way we do it no matter what n is. So notice I'm doing 0.29 divided by the square root of n. What's really awesome about this calculator is you don't have to memorize an extra rounding rule and like basically be like, oh, how much accuracy should I keep? Should I write down? I basically prefer to skip all of that. Let's just put the exact answer and let's round only at the final step. Okay, wow, look at this. Notice it has an e minus 4. So here's the way we round a question like this. We are going to basically say, okay, 9, we're going to grab 3 sig fig. In this case, we're going to grab the first 3 digits, 9, 5, and 6. And then I'm going to do e minus 4. So let's write this down on the calculator. And I'll show you how to write this. So first, let's just write down the calculator answer. 3 sig fig is 9, 5, and I'm sorry, 956 e minus 4. And then let's get this ready by just moving the decimal place 1, 2, 3, 4 spots to the left. The final answer is 0.0009. Okay, that's basically the 4 decimal places. And then I keep writing the 5 and the 6. Okay, I hope you can appreciate that is a really, really tiny probability. Now, here is why that's the case. So I already did one standard deviation right here, okay, using this decimal approximation. So I'm going to do the other ones off screen here. So it was 3.02 plus 0.058. Okay, just confirming that I did it correctly last time, and then plus 0.058. So the second tick mark is actually 3.136. And the third tick mark, which is hiding under the big bold marker, this is 3.194. Yeah, it's a little overkill that I didn't round these, but it's really helpful to kind of conceptualize what we're doing. Because remember, every dot under this curve is the average of a sample of 25 students and all of their GPAs. Okay, now, since that's almost, so the third tick mark's almost 3.2. Let's say 3.2 is just right above that, and then I'm shading everything beyond, which it doesn't really look like I'm shading it. And it's like, unless you know that I'm using that orange marker, you probably would miss it. Again, look at the probability. It's a super tiny probability. Okay, let me just kind of say a little bit more about this example. When you randomly grab a student from this school, right, you're going to basically imagine, well, most people will have GPAs kind of in the usual range. Usual range being basically somewhere in the middle, about 3.02. Well, it's going to be much, much harder for a group of 25 students to also have that same exact GPA, right? Because you've got good students, poor students, and all students in between, right? So if you're grabbing a big group of students, generally the GPAs will be a little lower. So to say, okay, 3.2 is a really good GPA, right? And if you look at this school, right? Let me actually work out the 3 markings for this one here. So 3.02 plus 0.29. So the second tick mark is 3.6. And then the third one, okay. So if you're saying, okay, a single student, the GPA is greater than 3.2, that's actually not super uncommon, right? There's 26.7% of the students have those GPAs. But to assume that in an entire group of 25, the average of all of those is above a 3.2, that's way harder, right? Because, you're going to have a lot of variation in those 25 students. Okay, almost done. We've got two more parts. Let's wrap up this example. So, part C, what does it say? Let's go a little quicker now. Find the probability that 10 randomly selected students will have a mean GPA between 2.9 and 3.0. Okay, the key here is 10. That's our n. N is bigger than 1. This triggers the sampling distribution. This time we've got a different n though. So the distribution's not exactly the same as in part B. It's a little bit different, but it's just a different x bar distribution. All right, well, let's go through this a little quicker. So probability of x bar. Oh, sorry, I shouldn't have written it like that. Since it says between 2.9, so that's our lower. So 2.90 is our lower. We want our x bar to be between that and 3.10. That's our upper. So our notation will reflect that. Normal CDF, lower, upper. Now, because we know we're dealing with the sampling distribution, we're going to need to do mu of x bar and sigma of x bar. But remember, we've got a different sample size n here. Our n is 10 now. Now, all of the means of the x bars are the same as the population, so we're going to put 3.02, just like before. Oops. What about the standard deviation? Well, that's going to be 0.29 divided by the square root of 10. So basically, looking at this, the only time the n really affects what we're entering is in that very last step. And remember, since standard deviation is affecting basically where we put these markers on the data set, essentially that's what it's changing. So it's going to give us a slightly different answer. Okay, let's do the calculation first. So second bars, there we go. Normal CDF, lower value 2.90, upper value 3.10. The mean stays the same. The standard deviation, 0.29 divided by, because our sample size changed, this is where we changed the number. Now, good news is we already had it there. So this is our answer. So pretty big, actually, 71 or 0.713. That's our probability that a group of 10 students. Actually, let me write that down real quick, and then let me just show you one more time how we get this. Let me go a little slower. So let's do second bars, normal CDF. Okay, so this part's okay. 2.90, 3.10. Type in the mean. Let me clear this one. Let's do this, the standard deviation from scratch. It's 0.29, that's the population standard deviation, divided by second x squared, so that we can pull up this square root button, and now we type in 10. And I just like closing the parentheses. I think it'll be fine if you don't add it. Okay, and then hit enter, and there is our answer. Cool. All right, so there's our answer. Let me just figure out the markings. Again, usually you don't need to do it, the markings, but I find them pretty helpful. So, um, give me 1 second. I'm just gonna do this off screen here. And I'm going to round here. So the numbers will be rounded. So this is 2.93, 2.84, 2.74. And then adding standard deviation up. It's actually 295, so it bumps it up to 30. Okay. So what we're saying is in a group of 10 students, their GPAs are between 2.9. So a little bit over here, let's say that's our 2.9. And then 310, so a little bit over here. So let's shade it. And looking at that, right, we have a much bigger part of the distribution. And it's kind of almost between -1 and 1. So 68% using empirical rule. It just turns out it's just a little bit bigger. And okay, that's just because we're sketching these, but conceptually it matches with the 71% that we got in our answer. So there we go. There's part C. Last part. And let's tag this part specifically as a super GTQ since I think that these questions are super important and they're interesting. So it says, would it be unusual, keyword for us, for 10 randomly selected students to have a GPA above 3.50? All right, so how do we answer that? Well, actually, what's kind of cool is I'm going to copy and paste the last problem because it's kind of similar. Let me just erase some of the details here. What we're saying is, okay, last time we had our students having GPAs between 2.9 and 3.10. Now we want GPAs above 3.50. Okay, so the way we'll compute that is with normal CDF. Actually, I don't know why I kept this. That's going to be different. So this time we've got a lower value of 3.50. Our upper value is going to be 1E99 because we don't have an upper value. Now, because it's 10 students, we get to use the same mu of x bar and sigma x bar as in the last problem. Okay, now what do I want to do? I want to take a screenshot. I'm just going to redraw it. So imagine our x bar distribution with our sample of n equals 10, 3.02, 1, 2, 3, 1, 2, 3. Okay, but maybe what I will do is copy and paste those numbers so I don't have to type them up again. Ooh, that matches pretty good. Okay, so where is 3.50? Well, I hope you see that it's way off to the screen over here. Right, let's assume that that is 3.50, and we want GPAs even bigger than that. From this, you know you're going to get a small probability. The question is unusual. Remember, what we're calculating is this is what's called a p-value. A p-value is calculating the probability of samples being either as extreme as the 3.5 or greater. So what is this p-value? Unusual means the probability is small. Remember, for us, that's the 5% cutoff. So, okay, time to calculate this. And let me just go to second vars. And 3.5 is my lower, upper. Let's hit clear. 1 dolphin button. Second comma 99 is my upper. And luckily, because it's the same mean and the same standard deviation, because our sample size is 10, I can just hit paste. And then this is our answer. Okay, so let's round it to 3 sig figs. That's 3, 0. Sorry, I can't talk. 8, 3, 1. And then E negative 8. All right, so write that down. 8.31 E negative 8. Okay, that is probability. Now, remember, that just means we're going to move the decimal place 8 spots to the left, which means it's actually 7 zeros. There's 6 zeros. Here's a 7, 0, and then an 8. So just pause the video and count. You can check that I've moved it 8 spots to the left. And then 3, 1. Obviously, that is a very, very small probability. So what we can say is, yes, it would be unusual for a random group of 10 students to have an average GPA above 3.50. Boom. That is our answer here. Okay, and that makes sense, right? Because you're grabbing students at random, and having a really high GPA is difficult. So you don't expect a random group of 10 students to have an average that high. Okay, well, that wraps up the series of videos on the sampling distribution. Thank you for watching. See you in class.